Hi, it's Ian. I think I have been out of town for a couple of months, but during that process there was a lot of head scratching, and thankfully there has been a good amount of progress being made, so here's an update video. As the last instrument that I worked with only have the tip size of half a centimeter by 1 millimeter, which barely gives me any room to work with. On the laser cutter front, I gained access to a much cleaner environment, which allowed me to make more stable samples. As with my school, because of the relatively more dusty environment, what happens is that the laser often gets obstructed by dust or some other factors, causing samples to differ from each other by a lot. However, in the summer, this of course changed. It's even one of those environments where you have to wear a disposable bathroom cap to get into. So first, let me introduce my first design. I made this during the spring term while I had a little bit of free time, and it's a pretty simple design, with only just a sensing area and a lead out section out of it. And with the new laser cutter in place, let's put it to the test. So the first parameter is resistance, the one on the bottom left corner, but on the bottom right corner that is called, what is X? I don't even know what X is. Let's check out what it is. Interesting. So what I found on Google is kind of interesting. Apparently X means reactance, and that in combination with the effects of resistance, it makes up what is called impedance. And impedance just means the effective resistance of a circuit to alternating current. And the general formula is that the magnitude of impedance equals to the square root of resistance squared plus reactance squared. It is exactly the same as the Pythagorean theorem. And reactance has two components. As you can see, there is inductive reactance and there's capacitive reactance. And each of them have their own formulas. So these two are just essentially describing for inductors and capacitors, in the sense that inductive reactance is how much inductors are resisting to alternating current and how much capacitors are resisting to alternating current. So now let's look further into reactance, as it looks a lot more better than resistance in terms of on the graph. It has more obvious trends, there is way less noise. You see resistance even has a weird dip at like 0.2 newtons, but reactance doesn't have that. And it has a stable baseline. And by baseline, I just means that when there's 0 newtons being identified, then it outputs the resistance value or the reactance value at that specific point. And so if we plot that out, we can see that reactance is pretty much superior to measuring resistance. However, after testing out a couple samples, I realized the baseline for them are a little bit different from each other. It's just all because of how laser-induced graphene itself does not create consistent pores. It's a little bit more like a randomized structure in some sense. And so what I thought is that maybe we can look at what is called sensitivity to understand how these sensors work. So now I want to measure sensitivity of these sensors. It's just described as dx over df, which is the derivative of reactance in respect to force. It just means that if I take every single instantaneous slope on the original graph and plot it to a new one against force once again. So this graph might look something like this, because we have a logarithmic original graph, which means that it's going to be having a high slope at many points, and then it's going to decrease as force increases. So I hypothesize it's going to look something like this. And if all of the samples are sort of consistent in this way, we can characterize it better. And we have a much more consistent way of measuring these guys instead of calibrating every single time if we want to put them on the surgical robots. However, there's still one thing bugging in my mind. As you all may remember, on the LCR meter inside of the lab, there is only X. There's no XC or XL. And so I think it is very important to transfer the LCR meter from only inside that place into a much more reproducible design, which means that it's time for me to make a DIY LCR meter that measures reactance and resistance. Let's talk about the circuit. The circuit is essentially a Arduino Nano, an LCD, a comparator, a 5-volt relay, and some various switches that does various functions, with the measuring sensor going in from this specific place. So this is all based off one single formula, which is F equals 1/2 square root of LC, You may ask, what is this even used for? So inside the LCR meter, we can see that there is an inductor with 100 microhenries. What that does is that it will only allow one variable to pass through, which is capacitance. If we know what the frequency of the LC resonance, then if we do some mathematical manipulation, we can find what the unknown capacitance and what the unknown inductance may be. Now let's talk about the most important component of the whole circuit, the LM311. It is called a high-speed differential voltage comparator. And what it does is that it quickly compares two analog input voltages and outputs a digital signal to indicate which input voltage is higher or lower. It features a very fast 200 nanosecond response time for fast switching, and the voltage range is actually pretty big. It's 3.5 volts to 30. That's almost a 10 times difference. And what it does is that it compares the voltages at pin 2 against pin 3. And if the voltage at pin 2 is higher than pin 3, the output will say high. Whereas if it's smaller, it will say low. Therefore, that we can set up a positive feedback loop. We can have an upper threshold voltage where the output switches from high to low, which will be inputted to pin 2, and we can have a lower threshold voltage where the output switches from low to high. And so as the measured capacitor, or as we call it, the unknown capacitor, charges towards the upper threshold, it's going to switch at the upper threshold voltage. And then it's going to allow the capacitor's discharge, and it's going to allow the capacitor discharge towards the inductor. And when the capacitor reaches to the lower threshold voltage, it's going to switch again, and the inductor is going to discharge towards the capacitor. And this cycle is going to repeat itself continuously, basically forever, until we cut out all of the power. I am still working on the circuit, but if everything goes smoothly, then we can measure the unknown capacitor, in our case the LNG sensor on the robotic arm, and use the LC resonant frequency to deduce what the capacitance is, and in turn know what reactance is. I have also made a couple other things to help with our prototype that I will demonstrate to you in our next video. Firstly, it is the Z-stage setup. I just used a Z-stage, it's essentially just the stage that moves up and down, along with a separator motor and Arduino. It's a pretty simple system. And next, just for some basic prototyping, I also built a separate ohm meter. And so this is what I'm currently working on, and after I finish the prototype, I would like to invite you guys to also watch a third video in which I showcase the full prototype in action. And that will be the time when I fully explain everything up to that point. So yeah, this is for the full update video, and I shall see you in the next one where the full prototype has been completed. I'll see you again.